So let's talk about polynomial ring in multiple variables just for a little bit. We'll need this not for too many things, but for now we just need this to give some rather non-trivial examples of maximal ideals and prime ideals, which will be the next topic that we study. Because if you just stick to polynomials in one variable, then because every ideal is principal, you don't get such a rich collection of examples. Once you get to more variables, things are richer. Okay, so here's an example of a polynomial in two variables, x and y. You're familiar with such expressions. One way to think of it is as a polynomial in one variable y, such that the coefficients are again polynomial in another variable. So you see, I can just take the y free terms, like this one, and this one, and that's a polynomial in x. And then I can take the terms that come with a y, like this one, and this one, and I factor out a y, and then I get again coefficient is a polynomial in x, and similarly y square, etc. And this is a more systematic way of writing it in increasing degree. So that would be one formal way of defining it, meaning if you just talk of real coefficients, let's say you have one variable polynomial ring, call it S, then you can define the two variable polynomial ring to be polynomial ring in Y, one variable polynomial ring with variable Y, where the coefficients come from S, meaning from Rx. Then you call this guy T, and then Rxyz could be polynomials in Z with coefficients in T, etc. Okay. So at any rate, let R be a commutative ring. With 1. And I'm going to denote by S the polynomial ring in n variable x1, x2, xn. And that thing is denoted by R, x1, x2, xn. Denote the polynomial ring in n variables x1, x2, xn with coefficients in R. And this is again a commutative ring with 1. This is S is a commutative ring with 1 as well. And you can add and multiply them in usual manner. So one way to define them would be to go one by one and define them inductively, like here. A typical element of S, f in S, has the form sometimes you write it as f x1, x2, xn, because you can think of these as n variable functions. Some element of the coefficient ring R times an expression like x1 to the I1, x2 to the I2, xn to the In. And this I1, I2, In all vary over non-negative integers. And these coefficients are going to be some element of the ring R, and they're going to depend on all these indices. So I'll write it as ai1, i2, in, where ai1, i2, in belong to R, and only finitely many of these are non-zero. So it's really a finite expression, even though I've written the sum over all non-negative integers. That's what a typical polynomial looks like. You can define degree in the usual manner. So a polynomial like this is called a monomial. x1 to the I1, x2 to the I2, xn to the in. Such a creature is called a monomial. So like x cube y is a monomial up here. And you define the degree of that, the total degree of that, to be just the sum of all the degrees. So like this term up here on the right has degree 3. And then you define degree of a polynomial f to be the max degree of all the monomials that occur in f with non-zero coefficients. So when I have written this polynomial on the right hand side here, I've written them in increasing degrees. This is the degree 0 terms, degree 1 terms, degree 2, degree 3, degree 4. So the maximum degree that appears is degree 4. So this f has degree 4. Right? So here is a degree 4 monomial that appears. Here is another degree 4 monomial that appears. Degree adds up when you multiply polynomials, as usual. And you still have this lemma that if R is a domain, then the n-variable polynomial ring with coefficients in R is also a domain. And this one follows immediately just by going one step at a time, because we already know that if R is a domain, then Rx is a domain. And now that I know that Rx is a domain, I'll know that Rxy is a domain. But that is same as Rxy. And so on. You can do an induction. Okay. So all that goes through as usual. The main thing that fails is you don't have such a nice division algorithm. There is a generalization of division algorithm, but it's very nuanced and it's much more delicate and not as straightforward and not as directly applicable as well. And the other thing that fails is that as soon as you go to 2 variable, these polynomial rings are no longer principal ideal domains. So in 2 variable polynomial ring, for example, we have the ideal generated by x and y in Rxy. This is not a principal ideal anymore. So the ideal structure is a lot richer. I want to mainly state this lemma, which gives you a tool to construct homomorphisms from multivariable polynomial ring. And a special case of this you have already seen. Basically, the fact is that to construct, the upshot is that constructing homomorphisms from polynomial rings are easy. You essentially have to just say where the variables go. So I'll state the most general thing first, and then part B and C will be special cases. So let R, S be commutative rings with R a subset of S, and let us give ourselves a bunch of things in S. Then there exists a unique ring homomorphism alpha from the n-variable polynomial ring to S such that alpha restricted to R, meaning if you take an degree 0 polynomial, is just identity. Because you see R is a subset of S, so I'm just going to not touch the coefficients, not touch the constants, so to say. The constants go to the constants, and such that alpha of xj is Cj. So if you don't touch the constants, then all that you can do is choose where the variables go. And basically you can send the variables to any arbitrary set of elements of S, and once you do that, you have no further choice. So in fact, alpha of a polynomial is just going to be the polynomial evaluated at C1, C2, Cn. A special case of this we'll need says that let's introduce a bunch of other variables. Let y1, y2, yn also be variables. And let's give ourselves a bunch of things in R. Then there exists an isomorphism from R y1, y2, yn to R x1, x2, xn, ring isomorphism, such that, call it alpha again, alpha of yj is xj minus cj. So you can do this linear change of variables, and it's an isomorphism. The fact that this defines a homomorphism follows from part A, but you can also define the map the other way pretty easily and check that they're inverse of each other. Part C is again a special case of part A, which I'm really interested in, and it's a special case when R is equal to S. So given C in R to the n, meaning n elements in R, there exists a unique ring surjective, in this case, ring homomorphism alpha from R x1, x2, xn to R such that alpha restricted to R is identity and alpha xj is Cj. In fact, we know this alpha, it's just the evaluation at C, i.e. alpha of f is just f evaluated at C, meaning f at C1, C2, Cn. That follows directly from part A. And part D says that the kernel of this evaluation homomorphism is the ideal generated by x1 minus c1, xn minus cn, these linear polynomials. So, because this evaluation homomorphism is a surjective homomorphism from Rx1, x2, xn to R, by first isomorphism theorem you get that if I take Rx1, x2, xn and quotient out by this ideal generated by the linear polynomials, this is isomorphic to R. And this will be rather crucial. And to prove this, you'll need part B. So the way I've written it, it looks long, but each step is easy. Okay? You prove A first, and B and C are special cases, and for D, you'll have to use B. That's all I'll say for now. And next time, we'll talk about principal ideals and prime ideals. Maximal ideals and prime ideals.